All right, 2 o'clock. Do today's static lecture. A couple of announcements. Homework 2, due at the beginning of lecture tomorrow. It's on 2D and 3D particle equilibrium, so make sure to take a look at that and get that in before 2 o'clock tomorrow to my email. We have your first exam for the class this upcoming Friday, obviously. If you didn't know that, where you been? The instructions for the exam are now up on Canvas. I kind of have a more formal sort of instruction guideline. So if you want to go ahead and take a look at that, I'll pull that up here quickly, maybe just so we take a look at it. But basically the idea is you're going to have open everything for the exam. And when you're doing the exam, I need you to turn the camera on for your laptop. You can keep the mic muted. Point it at your workspace, and so I can see you and kind of you doing your work. So this is basically the idea. The exam's going to be open everything. Prior to the exam, prepare your workspace, pencils, papers, whatever. Join the Teams lecture as normal. The meeting will be open at least 10 minutes before the regularly scheduled time. Turn on your camera, leave the mic muted, and point your camera towards you and your workspace. So here's like an example image of me in my guest bedroom performing my exam. All right. Basically, I just need to know that it's you doing your work. I just want to make sure it's, not your brother or your older sibling that's taken this class in the past doing everything for you. All right. I will post the exam to Canvas right at 2 o'clock. So it'll be posted under the exam information module in Canvas. So take a look at that right at 2. You don't need to copy down the problem statement or anything from the problem statement. Just get your white paper in front of you, write number 1, and just go to town. All right. You don't need to copy the problem statement or whatever. Just execute. All right. Then once you're done, you can submit it to me by email. So you'll have 50 minutes to do the test, your normal lecture time, right? 2 to 2:50. And then I'll give you an additional 10 minutes to email it to me, just like you would email me your homework solutions. So whatever method you typically use for homework, just do that same thing for your test and get it into me that way. Okay, so just as you would submit the homework. Please, no more than 10 minutes. All right, it's got to be in my email inbox by 3 o'clock. All right, I'll also be responsive to email and chat conversation during the exam time. So these exam instructions have been posted on Canvas if you want to review them again in a more detail, but I thought we'd just take a little bit of time to go over them now. That's the idea. So I will not be here in this lecture hall on Friday. You can come to this lecture if you want to do your exam here. That's fine. I got no problem with that. But I will not be here on Friday. I'll be monitoring from my home. All right, exam 1 review is going to be Thursday night. So we'll have a review session. A lot of people said in their first homework, some of those bonus questions, that they like the extra problems, they like the review sessions. So we'll have a review session on Thursday night. And that review session will be going over the practice problems that I sort of sent out for exam number 1. If you go to Canvas right now, you can find those practice problems. And I also, just a few minutes ago, uploaded my full handwritten solutions for those exam practice problems. So you got 9 practice problems there. Take a look at them, make sure you know them. If you can do all those practice problems, you will crush the exam like a tiny grape, okay? You will dominate. So if you can do everything on that exam review, you will crush. All right, so we'll meet at 7 p.m. on Thursday night, tomorrow night, if you'd like to come. That's not required. I'll record it and post it to YouTube if you want to watch it later. Not required, but if you want to come, we can do some practice problems. Okay, any questions from the chat or in the person, live persons? Okay, then without further ado, let us pick up where we left off. I'll just kind of remind you where we were last time. We were doing this example problem yesterday. We were looking at this crate suspended by 3 ropes, AD, AB, and AC, kind of suspending this particular crate or block here. We created a free body diagram, and the idea is we wanted to calculate what were the tensions in all these particular ropes that are keeping this block in equilibrium. Okay. So since we're in equilibrium, we could write that the sum of all the forces on this particular particle, in the middle here, this particle A, was equal to 0. So some of the forces X, some of the forces Y, and some of the forces Z equal to 0. This will give us 3 equations. But before we kind of go to those equations, we need to separate these forces in our free body diagram here into their components along X, Y, and Z. And to do that, we need to resolve all of those forces into rectangular coordinates using our unit vector methodology. And so we need to define unit vectors along the various forces. Here we're defining a unit vector lambda AB along this force AB. We're also going to define a unit vector along AC. And that's about where we had kind of left off last time. So we were sort of defining what each one of these vectors are. First, the weight, which is just going to be negative 40 pounds in k hat. We also saw that this particular force here is just in the x direction. So we could write that force AD as just the tension in the x direction, which was nice and convenient. But the two forces that are sort of at this weird angle, we had to write in terms of this unit vector that we don't yet know, lambda AB and lambda AC. So let's first resolve those forces into those rectangular components using our unit vectors, and then we can do our summation of the forces equal to 0. So to create these unit vectors, we talked about this last time. The unit vector between 2 points, we can sort of use the geometry of the problem to create this unit vector, and is this distance vector between 2 points of interest normalized by the total distance between those 2 points. That will give me a unit vector of magnitude 1 in the direction of that particular force. So we did that for force AB, and that's where we left off last time, and we're going to continue now by creating a unit vector along the next force of interest, which is force AC. So we did it for this particular force, this force tension AB, this particular direction. We also now need a unit vector here, which is lambda AC. So that's what we will do now. All right, again, we're just going to use this idea of the distance between 2 points. So from the particle A to kind of the hook in the wall C, where our tension is running, where our wire is running. Here we have point A, here we have point C. So the distance we need in X, Y, and Z. So in the X direction here, we're going backwards 3 feet. So we're going to have a negative 3I. In the Y direction, to get from A to C, we're going to have to go a positive 4 feet. So that's 4J. And then to go from A to C in the Z direction, we're going to have to go up this 8 feet here. So I've got negative 3I, positive 4J, positive 8K. Let me organize my stuff here a little bit better. All this normalized by, what is the total distance between the two? And again, that's just my distance formula, the square root of the sum of the squares of the components. Negative 3 squared plus 4 squared plus 8 squared. Units down in the denominator are feet, so units will sort of cancel out for this particular guy. And we get a vector in the direction of the force AC. That's going to be something like negative 0.318 I hat plus 0.424 J hat plus 0.848 K hat. Okay. And so this would sort of be our unit vector in the direction of the force AC. Now, we're finally ready for our equilibrium equation for this particular problem. All right. So let's just put all the forces in here for sort of a teaching moment, and then we'll show you how the 3 separate equations in the 3 different directions sort of shake out. So if we wanted to just sum all these forces equal to 0 directly, we would do something like the force of AD, the force of AE, AC, and AB, sort of all together. Right. So something like force AB plus force AC plus force AD plus force AE. All of these together have to equal 0 for my equilibrium to hold. It's a general idea. And so we already sort of wrote what each one of these particular forces is. I'm just kind of hammering this home for teaching purposes. So force AB, if we go all the way back up here, So it's this guy here, it's force AB. And that is just the tension AB in the unit direction governed by lambda AB. So this is TAB in the unit vector lambda AB. Adding to that FAC, which is the tension in rope AC, that's the magnitude of my force, in the direction of that particular force, which is along lambda AC, plus the force AD. Go back up to our picture here. AD is here. It's the tension AD solely in the x direction, so it's going to be TAD and I hat. Plus FAE, which is basically the weight of this guy acting downwards. So that's kind of this guy here. Let me sort of show that that's negative 40 K hat pounds. All equal to 0. Now these we know. So we could expand and sort of write these guys out. So let's do that now, just so we sort of see what's going on here. All right, so the tension in AB multiplied by the unit vector governed by AB. This is something we found last time. Negative 0.318 I hat minus 0.424 J hat plus 0.848 K hat. I'm going to add to that here, this component, which is kind of this force here. This is the tension in rope AC multiplied by the unit vector along AC, which we just found, negative 0.318 I hat plus 0.424 J hat plus 0.848 K hat. Looks very similar to the unit vector in AB. They're sort of like mirrored about that x-axis. It's kind of interesting. Now I'll add to it my component TAD I hat and my component here minus 40 K hat equal to 0. And so this looks like one equation, but it's really three equations. All right, one in I, one in J, one in K. And so what we're going to do is we're just going to separate all three of these guys into their three separate equations. All right, so let's go ahead and execute that now. So this is one in each of I, J, and K. So giving us some of the forces x equals 0, some of the forces y equals 0, and some of the forces z equals 0. Those are kind of our three equations that we're seeing here. One in I, one in J, one in K. They're in three sort of mutually perpendicular directions. So three sort of independent equations, one in each direction. All right, so let's go ahead and start pulling these things out. You can do it in any order, x first, y first, or z first. It will actually be easiest for us to do the y direction first, because this guy hanging out here in I, this guy hanging out here in K makes those two directions a little bit more difficult. So we'll actually start with the y direction, which is, you know, this J hat unit vector. So we'll start with some of the forces in y direction equal to 0. So I'm just going to basically pluck the components here for the y direction. And so we'll have something like TAB times negative 0.424 and TAC times positive 0.424. And we'll get a relationship there then between TAC and TAB. So here, negative 0.424 TAB plus the second component, 0.424 TAC. And those are my only two components kind of in the y direction here. So you can do some algebra here to actually show that from this particular situation, we find that the tensions in AB and AC are actually the same. It's an interesting finding. We always kind of want to check and make sure, like, does this make sense based on our picture? Is this reasonable, given what we know? So if we go all the way back up here to our photo, sort of AB and AC are sort of opposing each other about this XZ plane. And they're really the only two forces that sort of exhibit anything in the y direction, right? The weight of this guy is fully in, negative z, and this particular cable here is fully in x. And so because of like the symmetry of this guy and this guy, sort of being the only guys that are loading anything in the y direction, we would expect maybe that they would have equal contributions or equal tensions because they're sort of mirrored about that XZ plane. So kind of interesting to sort of see that sort of manifest in the math. Okay, so that's a nice finding there. All right, next. Let's move on to one of the other directions. We can go either way, but let's do Z first, since we actually have the weight of that crate. Can it help us? Okay, so I'm going to pluck this guy for the Z direction, 0.848 TAB. I'm going to pluck this guy, 0.848 TAC. And I'm going to pluck this negative 40, which, as a reminder, is pounds. Getting a little lackadaisical with my units. So 0.848 TAB plus 0.848 TAC minus 40 pounds. All this is equal to 0. From before, I know that TAB is equal to TAC. It's just kind of coming from here. So I can plug in sort of this relationship in either spot here. So we could do just something like 1.696, either TAB or TAC. It's all the same. Let's just say TAB for now. I'll swing my 40 pounds to the right-hand side. And here I'll get that the tension in AB be 40 over 1.696, which will be 23.6 pounds. And with my relationship that I found previously, sort of like the y direction, what is going on here? I could also write, sometimes it does this. I don't understand why. All right. Come on, writing pad, you can do it. I believe in you. Okay. TAB, this here is just 23.6 pounds. And we know from before, with our relationship in the y direction, the TAC is also the same thing, 23.6 pounds. Okay, so there you go. That's from some of the forces in the z direction. And then lastly, we can do some of the forces in the x direction equals 0. Hopefully my writing pad cooperates. What the heck, man? All right, I'm giving up. We'll just do it from previous history. Some of the forces in x equals 0, you can pluck these off yourselves. It's going to be something like negative 0.318 TAB minus 0.318 TAC, contribution from C, plus the full contribution of that force acting solely in the x direction, just TAD, all equal to 0. All right, so both of these guys I know. Both 23.6 pounds. If you like, we know both of these, so just multiply by 2. Plus TAD equal to 0. Work this down. You'll find that the tension of this sort of force acting in just solely the x direction is 15 pounds. Okay. So there we go, kind of figuring out what all the tensions are. So it's sort of using your 3D equilibrium. All right, we've got forces in certain directions. We figure out what the unit vectors are in each of those directions using sort of these geometric point-to-point relationships in the problem. That allows you to resolve the components of the forces into the various directions of the unit vectors, sum the forces in the directions, set them equal to 0, solve for the unknowns that you have. General idea. Okay, so we'll do one more example problem today, and I want to kind of work it as a class. So we'll bring it up here, and maybe we'll have you make the free body diagram, then we'll come back and do it as a class. Then I'll give you time to individually resolve the components, then we'll come back and do it as a class, and etc. Okay. So this problem here is very similar to like the flower pot problem from your review session. You have one that's very similar to this, I think the stoplight problem on your homework. So I'll bring this up here and we'll work through it. We've got this bucket here, total weight of 20 pounds. We want to determine the magnitude of the forces in these particular cables. This is looking a lot like the previous problem. And I want to see how well you guys can sort of do it on your own, executing as the class. So first things first here, let's make a free body diagram about point D and do our best to sort of draw those forces. And I'll come back in maybe 3 or so minutes and we'll see how you did. Okay, I'm gonna copy this problem over to the writing pad. Keep going if you're still working. I'll bring it. Second. Maybe another 30 seconds or so on the free body diagram, and then we'll work it. free body diagram this guy out, not all that difficult. Okay, so let's do it here. We've got kind of this point in space, and we're going to isolate point D. So we isolate point D, we're going to cut through kind of like 4 different ropes there. We have to make sure that we count for all 4 of those sorts of things. I'm going to put a coordinate system on here just to match the coordinate system of the problem. So here we have X, Y, and Z. So now I'm going to work my free body diagram. I want to make sure that I'm putting forces on here. The first and most obvious is going to be the weight of this bucket down here. So let's maybe just call this W with the bar over it. Weight is a force vector, so let's make sure that we write it as a vector, W bar. Next, we have this force that's acting kind of like in the negative Y direction between D and B. So kind of cutting through this rope here. That's kind of solely in sort of the negative Y direction, but I'm just going to label this right now as F from B to D. I've got this guy here coming off of D, just kind of like coming out at me. It's a little bit hard to sort of draw this in 3D, but do your best. Here's FAD. And then finally we have CD that's kind of like pointing backwards. Again, a little bit hard to represent in 3D. Just do your best. Feel like Bob Ross. Like, I know it's hard to sort of draw in 3D, but do your best. I'm not good at it, but I enjoy it. I'm like the Bob Ross of drawing free body diagrams. Let's put a little tree over here. How about we put a little tree in the background? Happy little tree. Question from the audience. He says, is there a difference in writing FBD or FDB? Not yet. In higher level classes, when it's important to sort of distinguish the directionality of the force, you might see it represented in a specific way. More important is when you get to higher level classes representing position vectors appropriately. So you'll see in future classes that you're going to have something that, if I'm interested in this point, let's call it point E. And I have some position vector that locates E from D. This is usually going to be labeled as something like the position vector R locating E from D. And that's just very specifically done so that you know you're pointed in one specific direction. In this class, it's not as important to be specific about the directionality. So sort of how you label your subscripts, I'm not going to be too picky about in this class, but in future classes, you will see this and it will be a little bit more important for you. All right. So here's our free body diagram, the nice tree in the background. Let's get rid of our Bob Ross tree. And let's kind of put some specificity to each one of these. And what do I mean by that? Well, let's let W, something we know, represented as a vector in our free body diagram, going to be the weight of our piece, which we know is 20 pounds, and we know that it's generally in the negative K direction. So here I can write straight away that this is negative 20 pounds K hat. Let's do the best that we can with the other vectors that we have to sort of represent their directionality. And then we'll use unit vectors maybe that we need to define with geometry to help us on our way where we can't quite fill in all the gaps. So FAD, I can represent this force as a force with magnitude and direction. It's got magnitude, which is the tension in the rope AD. We label it as TAD. And I don't really know what direction it's in at this particular point. It's not obvious that it's in, just the I or J or K directions. So we'll just represent its directionality as lambda AD. and sort of come back to that lambda AD in just a bit here. Fbd. This one's a little bit easier to handle. This vector here is solely in the negative j. So I can just represent this as TBD, solely in negative j hat. Or you might see it as negative TBD j hat. That's nice, because I don't have to sort of like fully define some random unit vector for this force. And you might look at CD, obviously is the tension. CD is kind of what we're after in this problem. And I don't necessarily know where that's pointed quite yet. So let's just say that this is pointed in an arbitrary direction, which is a unit vector defined along the points between C and D, lambda CD. So I'm looking for the tension AD, the tension BD, and the tension CD in this problem. And I'm going to enforce equilibrium. But before I sort of enforce equilibrium, I need these unit vectors lambda AD and lambda CD. These are unit vectors that sort of like run along those directions between points AD and points CD. And so let's give you maybe 5 minutes now and see if you can sort of come up with those unit vectors. So here, your next task is find this lambda AD and lambda CD based on sort of what we've done before. And I'll pull the picture up here and just so you have it as a reference. So we want lambda AD, which is a unit vector along this direction. And we want lambda CD, which is a unit vector along that guy. So see what you can do to sort of solve for those unit vectors. Let me give you a couple minutes here to give that a go. And I'll give you a reminder on what that equation is going to look like. That's kind of the equation that you want to utilize here for both of those guys. I'd say one of the biggest problems or mistakes that I see on the first exam when I teach this class is defining this unit vector lambda. You're going to have to use the geometry of the problem a little bit. Make sure you execute this appropriately. Maybe go until 2:37 on the clock. Oh, it just turned 2:36. Maybe we'll go till 2:38 on the clock. Okay, 2:38. Let's give this a go. So we'll first start with lambda AD. And my general formula is here. And we'll remember that this dx, dy, and dz represent the distance that you have to travel from point to point to get from one point to the next. Okay. So for instance, lambda AD, if I'm looking at the distance I need to travel in x dx to go from D to A, I'm starting at D and I want to end up at A. Well, point A is at 4.5 feet in the x direction, and point D is at 1.5 feet in the x direction. So to get from D to A, I had to move 3 feet in x. So the dx component in this particular situation for lambda AD would be 3 feet. Right? Let's look at dy. Similar idea. If I'm going from D to A, point D is kind of like in the y-x plane. All right, so how far did I have to sort of go in this y direction to get from D to A? Well, A is 1.5 feet behind D. So I had to go a negative 1.5 feet here. All right, and in the z direction, here's sort of the z direction. I'm in the xy plane for point D. And so we can see if I wanted to go from D to A, I would have to move up 3 feet to go from D to A. So here, this would be a 3 feet for my DZ. So it's a little messy there. I'm going to put it all together sort of in the bottom here, and we'll write lambda AD. I had to move 3 feet in I hat. I had to move backwards 1.5 feet in J hat, and I had to go up 3 feet in K hat. I'm going to normalize this by my total distance of this particular distance vector, which is just going to be 3 feet squared plus negative 1.5 feet squared plus 3 feet squared. Or if I work through this, 0.667 I hat minus 0.333 J hat plus 0.667 K hat. Nice round numbers. You could use 2/3, 1/3, 2/3 if you want. I like working in decimal for these unit vectors. Just makes me a little more comfortable. They're not always going to be nice fractions, so I just like to work with decimal. We're going to go through a similar process when we're defining our unit vector between points B and points D. Right. So I first want to define what is the x distance traveled, y distance traveled, and z distance traveled between D and B. I'll go back up to my figure here. All right, so here's D. Oh, I wrote B, I meant C. Sorry about that. C and D. Okay. Well, to get to C from D, I'm starting at D going to C. I'm going to have to go backwards 1.5 in the x direction. In the y direction, point C is at a location 2.5 feet, and point D is at a location 1.5 feet. So I'd have to split the I'd have to take the difference of those 2 points to know how far I move in y to get to C from D. So that would just be 1 foot. I'm going to drop the feet for now. And then finally in the z direction, point D again is in this like xy plane. So to get to point C from D, I have to go up 3 feet. All right. So this will be plus 3 k hat. All right, units on this are feet. I'm sort of dropping the units because they're going to cancel anyway. All normalized by the total distance of this vector, negative 1.5 squared plus 1 squared plus 3 squared. I think this is the hardest part about these 3D problems, defining these. So I know I'm taking quite a bit of time to talk about these unit vectors, but it's probably the hardest part of these problems. Work through this, negative 0.429 I hat plus 0.286 j hat plus 0.857 k hat. So those are your unit vectors in the 2 directions, AD and CD. Okay. Last thing we want to do, sum of the forces equals 0. So let's do that quickly. That would be something like FAD plus FBD plus FCD minus my weight, or I guess plus the weight, since we sort of drew W in the negative direction. This is equal 0. That's my general formula. If we write this in terms of the magnitudes and directions, TAD lambda AD plus TBD, I guess lambda BD, even though we know we're kind of in the negative J direction. So here I'll write TBD negative J hat plus TCD lambda CD. And then just to put a cap on this, this is minus my weight of this guy. Let's just do plus 20 pounds. And this is a negative K hat. We'll just be very clear about the magnitudes and directions sort of being separate for now. All right, I kind of now have these guys. I can plug them in and we can work with this directly. So TAD times the unit vector defined by AD. We have this already, 0.667 I hat minus 0.333 J hat plus 0.667 K hat. So my unit vector in along AD. Here on minus TBD J hat. It's tension in route BD. Add to this the tension in CD multiplied by the unit vector along CD. Calculated this already, negative 0.429 I hat plus 0.286 J hat plus 0.857 K hat minus 20 pounds in K hat, all equal to 0. I'll enforce my equilibrium again. Look at components in the I direction, components in the J direction, and components in the K direction, sort of as 3 separate equations. One in I, one in J, one in K. And we can make our way through these 3 equations. I know it's really only got 1 equal sign, but this is actually 3 equations. So we have 3 equations, 3 unknowns, TAD, TBD, and TCD. And I have 3 equations, I, J, and K. And we're just going to solve simultaneously. Right? So sum of forces. X equal to 0. F 0.667. TAD, just kind of like plucking this guy here. Minus 0.429 TCD, plucking this guy. And those are the only X components that I have here. I can't solve for each of these directly, but I can come up with a relationship between the two. So you can sort of solve for one of the 2 variables here, and we'll kind of plug it in later. Here I've done TAD is equal to 0.643 TCD. Okay. Maybe we call this star, and we'll use that later. Sum of the forces Y equals 0. So here I'm going to pluck the negative 0.333. I'll pluck this guy. I'll pluck this guy. Minus, I have all of my tension of BD in this general direction. And then plus my contribution from CD, which is 0.286 TCD. This all equals 0. I can make this substitution here. I can simplify down and get another relationship between CD and BD. If I do that, I'll get a relationship is TBD is 0.072 TCD. Just kind of plug and chug. It's kind of like freshman level algebra, I guess. Pre-algebra, I guess. And then lastly, my final equation, sum of the forces Z equals 0. Plucking those individual components from the sum of the forces equation above. 0.667 TAD plus 0.857 TCD minus the weight of my bucket, 20 pounds, all equal to 0. All right. So I can use star here, and I can use double star here, if I'd like. And you can whittle this down with some substitution to TCD is equal to 15.6 pounds, which is one of our answers. Okay, and then back into star. And double star will yield you the other two tensions. And that is TAD is 10 pounds. And TAB, sorry, BD is 1.1 pounds. All right, so once you get through the unit vectors, it's just kind of like some very good note keeping, meticulous algebra, plugging in correctly, making sure that you're not making calculator errors, all that stuff that makes a good engineer, right? Keeping track of your units and all that good stuff, right? So that does it for today. 2 minutes over. Apologies for going a little late. We'll have a review session in class tomorrow, and don't forget we'll do practice problems in the evening at 7 p.m. So see you then.
I actually have a question.
Question? Yes, go ahead.
So I did it differently. I just I took the coordinates of each individual point and then I did D minus like A, D minus B, and D minus C, and I got like the reversed like signs. So instead of positives, I got negatives.
Uh-huh.
Would that still be the same answer? Or would that be a different answer?
You're still going to find the same answers. You're just like basically all of your signs are going to be flipped, but it will still work out. Okay.
Okay.
So if you just track everything correctly and you work through it correctly, you should still get the same answer.
Okay.
Cool?
Yep.
Okay. Take care.